We are on chapter 21. Electromagnetic induction. So, in chapter 20, what we saw was all about magnetism, right? We saw the magnetism part of it, and we saw how a current-carrying conductor produces a magnetic field in the neighborhood, and we found out different situations: a straight wire, what is exactly formed, a flat circular coil. Then you have a solenoid, what happens in the solenoid, and then we kind of put everything together, and we found the force on a conductor placed in a magnetic field and carrying current. We defined the Tesla, right? We defined the Tesla, and then we found out also the force on moving charges. So you know exactly what to do if there's a charge that is moving in a magnetic field, how to use that. You know, force concept, F is equal to BQV, and because of that force, it turns into a circular path and all that stuff. And then we also used the concepts into the Bainbridge mass spectrometer. And we saw how the spectrometer was doing the job. So in all, the stuff that you've done so far is right-hand grip rule and Fleming's left-hand rule. Those are the two things that you've done so far. Now what is covered in chapter 21 is electromagnetic induction. So put everything in short. This is what it was. If there's a current flowing in a straight wire like this, if a current is flowing like this, will it create a magnetic field?
Sure.
Yes. Which way is the magnetic field here?
Well, if you do,
It's in. All right? So Faraday was trying to think the other way around. He said, okay, if I send a current through a wire, it is producing a magnetic field. Now, what if I just keep a wire and I don't send a current through it, but if I keep a magnet right there, if I keep a magnetic field,
current.
So will a current flow here? That is what Faraday was trying to think. So he was trying to think the opposite. A current-carrying conductor produces a magnetic field. Can a magnetic field produce a current in a wire? That means you can generate current. That was a concept that he was thinking, he was trying to get. And in that process, he was trying to, to create a magnetic field. The best way to create a magnetic field is to use a coil and magnetize something, right? So Faraday kind of designed his own little instrument, and that is he took a bunch of metal wire to act as a core, just a bunch of wires, and on this wire he wound electrical wires like this, and he connected to a battery. So when he connected this to a battery, will this get magnetized, this core? Because when you pass a current like this, look, the current is flowing like this, and it is like a solenoid. And what is inside the solenoid is a ferrous material. So it is definitely going to produce a magnetic field. So it will produce a magnetic field here. Which way? Of course, you have to use your grip rules. So I've not drawn it three-dimensionally, but one thing is sure, that this will produce a magnetic field either clockwise or counterclockwise. So it is definitely producing a B inside. And that B is definitely going to be going here, right? So the magnetic field is actually going through the core continuously. It's kind of looping itself. So this current is creating a magnetic field in the core, and because the core is here, the magnetic field should be going through it. And then what he did was, he took another wire and he wound it over it. He wound another wire over it, like this. And he didn't connect this to a battery, instead he connected to a galvanometer. the galvanometer like that. He connected to a galvanometer to see, what is the galvanometer's main purpose? To detect currents. Right? He wanted to see the current. So he connected to a galvanometer, hoping what? There may be current here. Why? Because you're subjecting this coil to a magnetic field. You're making a magnetic field go through the coil. So the coil must be getting some current. So he wanted to desperately see if there's a current in this galvanometer, and he was disappointed because there was nothing. So there was no current here. And when he was disappointed, I was looking for a current like that, no current didn't come through. So in his disappointment, he wanted to kind of, dismantle the whole thing. And when he wanted to dismantle the whole thing, he started from here. He just disconnected the wires of the battery. As soon as he disconnected the wires of the battery, he saw something happening there. Then he connected the wire, and then he saw something happening there. So the galvanometer was deflecting only while he was connecting or disconnecting, not when it was permanently connected. So when he was removing this needle was like one deflection. That's it, and back to normal. When he connected it, it went the other way and back to normal. When he connected and disconnect, disconnect. That was what was seen. Okay? Do you get it? That was exactly what Faraday discovered initially. That yes, I'm able to get a current, but that's not a direct current. It's an alternating current. It's going both ways. Make sense? Now, instead of connecting and disconnecting, he put a rheostat here. You know what a rheostat is? Right? He put a rheostat here. And by sliding the rheostat, what is he doing? Changing the resistance, thereby changing the... And when he was doing that, there was a current here. When he was reducing the resistance, the current was going like this. When he was reducing the resistance, the current, this deflected for a little while. And when he increased the resistance, it
What is that called? The resistance changer, what is that called again?
Rheostat. Variable resistor, another word of. So this is a rheostat. You can just have a variable resistor, That's a rheostat also, but it is circular, like the volume control. See, it's turning now. Right? I told you about this, right?
Yes.
Yeah, this is 10 kilo ohms. It says 10 kilo ohms, and this is a very old component. So it's 10 kilo ohms. So if I connect a multimeter here from here to here, and when I turn it, it will be changing. Just like a rheostat, but it's called a potentiometer. Yeah.
What? God, I'm sorry.
Yeah.
Chill. What happened when I connected the rheostat?
Oh, but connecting the rheostat is not the main thing, but changing the resistance of the rheostat made currents here.
Okay.
So what Faraday discovered was this. If the current here was changing, then there was current generated here, as long as it's changing. If it is fixed current, then nothing is happening here. So Faraday discovered that a changing magnetic field can produce a current, not a fixed magnetic field. You get it? If the magnetic field is changing, then yes. Now here's a galvanometer. Okay? And in this I think you can see clearly the coil and the springs. I think I should have done this one earlier. You can see it much better on this. You can see the coil and the magnet, the shape of the magnet, everything. This is the galvanometer. And here are 3 sets of coils, like this. Like this. Just 3 sets of coils, all of them are connected to the galvanometer. So if I take a magnet and put it inside one of them, nothing is happening, right? But when I change the magnetic field, do you see the deflection?
Yes.
Now I'm putting it back in.
It's ridiculous.
Take it out, put it back, take it out, All right, do you see it? So the deflection is one way or the other way. So it depends on which one I'm doing. Now, if I'm putting this end inwards, it is deflecting the right. But if I put this end in, it should go to the left.
What?
You understand that?
Not real.
Okay. Now, of course, this is not going to create too much of a deflection because of less number of turns.
How come his fingers on the needle?
Yeah, exactly.
Where?
I see your finger on the needle. I see it. No. What's some trickery?
Some tricks going on.
It's right there. You see the two wires? Yeah.
That's a needle.
Oh.
Where are you looking at?
Come on, where are you looking?
Okay.
Anyway.
So you can see how it's deflecting nicely here and less here and lesser than that. And the reason is number of turns. Because number of turns are also equally important in this. So if I have lots of turns here, I can get more deflection there. So Faraday ended up discovering that the change of magnetic field is what causes induced current. It's called induced because you're creating a current due to some action here. That's called induced. You can induce a current in a neighboring wire because of a change of current in the first wire. That's induced effects. It's like two students sitting in a class, neighbors. If one student does well, the other one gets motivated to kind of do better or try to put more effort into it because one is doing well. And so the performance of one will be dependent on the other. So sitting next to a bright student will make you brighter. Sitting next to a dumb student will make you dumber. Simple as that. What is motivating you? What is motivating you is a very, very important factor, even when you go to college. So select your friends accordingly. Select your friends accordingly. It's very easy to kind of easily fall off from your expectations and things like that, all because of just one fellow who actually ended up having some problems and all that, and then he is now your friend, and so you kind of drift into that same mindset. It is not your mistake. I mean, it is an induced effect. It's an induced effect. So that's why it's always good to be around someone who you like to really be also. So trying to get close to someone and then trying to establish that connection, that's pretty important. So having good friends who are free from drugs and alcohols and anything like that will be beneficial to you. Whereas if you have friends who are actually, of a different type, then now if you have friends who are actually spending hours and hours on video games, then you end up getting attracted to that playing games concept, and then you end up playing. And you without even realizing that you're already there.
Do you ever play
video games?
Red Dead.
You don't play. You should pick up a good video.
Fortnite.
I don't like any.
Would we consider the flight simulator a video game?
It's not a video game. It's more of that is a different thing.
That's a video game.
Anyway, so Faraday ended up discovering this. Faraday ended up discovering that if there is a magnetic field fluctuating here in the core, just like as I did here, then you can expect an induced current. So he came up with his ideas. Now, before I tell you his actual statement, let me explain to you the word flux. Okay, I'm taking this off. Flux and flux density. Flux and flux density. The word flux is simply trying to tell how crowded are the magnetic lines through a coil. So if I have a coil like that, and if there's a magnetic field, that's a magnetic field. How much of these field lines actually are able to pass through the coil? See, that is the flux. We call it flux. How many lines, literally? How many lines? You know that lines are imaginary, so it's a different. It's something that you have to relate to the crowding of the lines. Okay. Now, flux is given by the symbol phi. Right? You've seen that somewhere? I don't think we used it.
I think we've used it like once.
Yeah, you don't fall.
When?
I think it was 2 chapters ago. Maybe.
Oh, in the electric field, yeah. So this is magnetic flux, though. This is magnetic flux, phi. And flux density means like how crowded they are. So therefore, you relate it to the area. Now understand this, that every loop of wire is subjected to the same flux. So if I have more and more number of loops, like in the example I showed you there, if you have more and more number of loops, there will be more and more flux passing through. Make sense? If instead of having one loop, you can have more number of loops. So you're having all the loops connected in series, and you're getting more flux linkage. We call it flux linkage. Yeah.
So flux is just how many field lines pass through the pole?
Sort of, yeah. The connection between flux and the field is that. So, what is this flux density? That is simply B. That's a magnetic field. And therefore, B is flux density. When you say flux density, you're talking about flux per unit area. So the more flux passing through a certain area, more field. That's a straight understanding of that. More flux passing through means more field through the same area. Here is another example. Suppose you have a magnet here, north, south. The magnetic lines that are going from here are like that. That's how the magnetic fields are from the North Pole. So if I have the North Pole like that, what is in front of it are field lines. Wow, a bunch of them. You get it?
Yeah.
Now, if I take a coil and keep it far away, that's a coil I'm taking and keeping it far away. How much flux is passing through that coil? Very little. So, if the coil has an area A, you can see that just one magnetic field line is just kind of passing through comparatively. As I said again, these are all imaginary lines. You can have more lines drawn in between. It's a representation. Now you can see here that this coil is linking only one line. Therefore, the flux density is less, which means the field over here is weaker. Make sense? Now if I move the coil here, if I move the same coil here, is it linking more flux?
Yes.
So the flux density is higher, and so the B is higher here. B is the flux density. So you have more lines per the same area, then more flux density. So more B. The closer you move, you are linking more and more flux. More flux. A lot of flux. Right? The flux density over here is pretty strong because you're getting closer and closer to the field, to the source. So the flux density is getting weaker and weaker. So how do you know a flux magnetic field is weak in a certain region? Just see how spread the fields are. That's it. If the fields are very spread out, that means the strength is weak. If the fields are crowded like this, that means it's strong. Make sense? Now, the unit of flux, is Weber. And in short, we just write WEB. The unit of flux is taken as Weber, and Weber is just WEB. And so if you look at the units there, if you look at the units here, what is B's unit? Tesla is equal to Weber per meter square. So the connection between Weber and Tesla is right there. Weber per meter square. That is Tesla. So this is a unit, okay? Tesla. All right.
Right. What's the Weber?
Yeah, Tesla is Weber per meter square. That's the unit of magnetic field. That's why sometimes we call this magnetic field as magnetic flux density. You get it?
Yes.
So the B, the unit is Tesla. And sometimes this B is called flux density. The B is called flux density. So you'll see in some problems, they'll say the flux density is so much. It's basically telling you the B. All right? The flux density, so or even in the explanation, it will say the flux density here is higher than the flux density. So it is basically telling you the magnetic field strength is more. Yeah, so flux density. And remember, when you're talking about how much is the linkage, you're talking about just one loop. So through one loop, the linkage is this. Through one loop, so looking at this equation, cross multiply, you get phi is equal to BA. This is for one loop. And therefore, for n turns, the flux is equal to BAN. Flux is BAN. And of course, there's another factor. There's another factor. It's not always going to be BAN.
Do not give me that sign,
Sign
data. Don't give me that.
Yes, sir. Yes, sir.
Always.
Yeah, because the coil, if the coil is placed like this, you see the entire area.
Yes.
But if I keep it like that, you don't see any area. So that means if I keep a coil over here, if this coil is placed like that, if this coil is placed like that, huh?
Why would you put it?
Is that 90 degrees?
That's yeah. This is like this, and this one is this one.
Magnetic field is going on.
Make sense?
I understand.
So these are magnetic field lines going that way. In this picture actually says, in this one it says the coil is like this.
Okay.
So it intercepts the whole area. But when I keep it like that, it doesn't see the area at all. So zero flux.
Yeah.
Zero flux.
Okay, so the flux can actually change from a maximum of BAN. This is maximum. So this is max. And 0 is the minimum. 0 will be the minimum flux. So what was happening when I did this? What was happening when I moved this magnet? When I'm far away, the flux was
0.
no. When I'm far away, like the flux density over here is less. The flux is also less. But I get closer and closer. The flux increases because I'm getting closer and closer. And when I'm pretty close, then the flux will be highest. You get it? So that's why when I change from here to here, well, I'm not supposed to move it myself. So okay. So it's not going to make any difference here. But when I come closer and make the same movement, it should be higher. Where am I? Yeah. All right. So Faraday came up with his. All right. So how do you find out the flux if it is a different angle? For that, what you need to do is the angle we are considering over here is the perpendicular to the plane of the coil. This is the perpendicular to the plane of the coil. This is perpendicular. You understand what I'm saying? Like that.
Yeah.
So perpendicular to the plane of the coil. If the angle between the perpendicular to the plane of the coil and the magnetic field is 0, that means you have maximum flux. Because cosine 0 is 1. When I turn it like that, the angle between this perpendicular and the magnetic field is 90. Cosine 90 is 0. So the flux linkage actually has a cosine angle component. So you can write that down. So flux is equal to BAN cosine of the angle, where theta is the angle between the magnetic field and the perpendicular to the plane of the coil. So the angle theta is the angle made by the perpendicular. This is the perpendicular to the plane of the coil. And when that angle is 0, you have cosine 0 as 1. And when you turn this like that, magnetic field is still staying the same way. You see lesser and lesser area, and that is controlled by that. So BAN cosine theta, this is basically the flux. So what Faraday came up with as Faraday's law.
What's the guy's name?
Faraday.
Can you spell that?
Faraday's law of electromagnetic induction. So he came up with a law now. And the law he came up was this. So it's electromagnetic induction. So what is being induced actually? What is actually induced?
Current.
But where can the current come from? No. What is needed for a current to flow?
Coulombs.
The
Electrons.
Potential difference. In other words, EMF. You follow that?
Yes.
If a current is being generated, that means the first thing which is generated before that is the EMF. So Faraday's law actually states about the EMF. So write down. The EMF is directly proportional to the rate of change of magnetic flux.
Easy.
That's what Faraday came up with. All right, this is the basic thing. Now, EMF is the main cause for the current. So this current that is flowing is because this EMF divided by the resistance and stuff like that. So current is a consequence of the EMF generated. So what is being generated is the voltage, the EMF. And what Faraday said is the EMF generated is directly proportional to the change of flux and also depends on how quickly the flux is changing. Make sense? So EMF is proportional to D of BAN. So the induced EMF depends on what? You can see that very clearly. The induced EMF depends on what? How strong the magnet is, right? How much area you're using. Now, there's no point in making the area big and the magnet is such a small magnet. Because then there's no change of flux. Make sense? If I have a big area like that and the magnet is kept here, that big area is trapping all the lines there as well as here. Literally all the lines. So is there a flux change? No. So if you want flux changes, you need to have magnetic field throughout the area. So if I'm going to take a coil that is that big, I need big magnetic fields also. Otherwise you cannot, in other words, I can't use just a tiny magnet for a big area. All right? So it should be sort of proportional. So the bigger the area where magnetic field is available, you can expect more EMF. The number of turns, it matters. That's why over here, when you have this one has more number of turns, and so it will produce more deflection. Now the angle, of course, is a changing thing, because if I'm going to spin, look, again back to this. Instead of making the magnet go in and out, I can actually keep the magnet in one place and just move the coil. You understand? Keep the magnet in a fixed place and move the coil. Move the coil away from the field. It's not easy to show here. I mean, imagine this is the coil. I can just spin the coil. If I spin the coil, I can get change of flux. Because if it is like this, what's the flux? BAN. If it's like this, 0. So it is changing flux. And if I do this, how much is flux? Negative BAN. Who said that? Good. So it's BAN, 0, negative BAN. So from here to here, what's the change of flux? 2 BAN.
That's ridiculous.
Yeah. Yeah, get to the root of exactly what's happening, and then you'll be like, oh, I understand what exactly is electromagnetic induction. You know what to do. All right, so look at this. That's an important factor too. How quickly the flux is changing. That's important. And you saw that here. How quickly the flux is changing. Like if I'm going to make this move very slow, you saw the deflection, right?
Barely.
Barely. But if I do it faster, like, see, it's fat more. If I do it really fast. Okay, did you get it? So the faster you change the flux, in other words, the shorter the time, more EMF. So if it is a coil like this, if I spin this coil in a magnetic field slowly, it produces a smaller EMF. But if I spin it faster and faster, it's going to produce more and more EMF. Make sense?
Yes.
Your alternator in the car. Your alternator in the car is basically driven, belt driven from your drive itself, right? So when you're driving the car slowly, the alternator is not spinning fast, so it's not spitting out high voltages to charge the battery. It's not doing much. But if you're driving faster, it will create more EMF because it's spinning faster. And that's why when so even the headlights will change its brightness. Headlights will become brighter actually when you're driving faster. When you're just idling your car, the headlights are barely lit. However, it's much better these days. But at least what I'm trying to say, or a bicycle dynamo. Have you seen a bicycle dynamo?
Like the little light on the front?
Yeah.
I've seen one. But
Not the battery operated ones. I'm talking about bicycle dynamo, which actually has, there's a kind of headlight. And the headlight is powered by what? It's a dynamo which actually sits on your rear wheel, not for racing cycles, normal bicycles. So the dynamo is actually something that spins. The coil is fixed, but the magnet inside spins. The magnet spins inside. And where is this touching? It's touching the rim of your
Tire.
not the tire.
Wheel.
The wheel, yeah.
Spokes.
Not the spokes. The metallic part before that. So when it is touching that one, as you start moving, it starts spinning. And it generates voltage. So if you're actually like driving faster, if you're moving faster, you'll see the headlights are bright. And if you stop, the headlights go down to zero. I'm not talking about battery operated ones. These days, it's all LED, battery operated, just flip the switch. But that one, and the same way you have those flashlights. Have you seen those flashlights?
Yeah.
And then it works?
Yeah.
What is that?
Yeah. Oh. I did not know that.
The flashlight, how you shake it and there's something that's moving inside, right? What's moving is a magnet going into the coil, back and forth. So when you do that, you are generating the current, and that current is used to charge the battery inside. And so after doing it like that for some time, you get it. And some of them are like, like you're basically spinning the magnet by either squeezing action like that, like have you seen that one? It's a flashlight, but it's got an arm. It's got a lever.
Oh yeah. No,
You pump it up like that.
You can hear it spinning.
Oh, you can hear it spinning. Perfect.
Yeah,
Yeah.
while you do it.
So those are all dynamos basically. So yeah, crank radio. Yeah, there are some cranking radios, and what you're doing by cranking is generating the EMF to charge the battery, and then that is so after cranking for some time, you have enough charge stored. It is going to give you the energy. All right. Now Faraday stopped here. Faraday was so happy that he came up with something.
you don't stop.
And he actually he was so excited that he came up with Faraday's law, which says EMF is directly proportional to the rate of change of magnetic flux. Have you written it down in words? The EMF is proportional, you can write down in words, EMF is proportional directly to the rate of change of magnetic flux. To the rate of change of magnetic flux. That is Faraday's law. And since he was very excited about his discovery, he just took a vacation. But people, the EMF is directly proportional to the rate of change of magnetic flux.
Alright, thank you.
Rate of change of magnetic flux. You can see all that here. The EMF is proportional directly to the rate of change of magnetic flux.
Okay.
Okay. Now, he kind of did not think about this any further, but there are people who are thinking. People are saying, all right, now, let's find out why it was going the other way around. When he put the magnet in, the deflection was one way, and when he put the magnet in, the deflection was one way. When he pulled the magnet out, the deflection is the other way. Why? Isn't the flux changing the same way? Now, what is happening there? There is some connection. And then they came up with the equation E is proportional to minus d phi over d. And the minus sign, minus represents Lenz's law.
So lenses can't figure out anything on his own. You're telling me.
So he was investigating where Faraday left. Faraday just mentioned this, but Lenz, and there's another person called Newman. He was also along with him. So sometimes this thing is called Lenz and Newman law. But Lenz is always like more popular for some reason. But these two people were in different parts of the world though. They were in different parts of the world. As soon as Faraday came up with his idea, both of them basically were thinking and researching about why opposite directions. And they both came up with this. So what is Lenz's law? Write down the statement and then I'll explain. Lenz's law. The induced current, you can write it down, the induced current as a result of induced EMF always flows in such a direction so as to oppose the cause. The induced current as a result of the induced EMF always flows in such a direction so as to oppose the cause. That's Lenz's law. And that's why the minus sign is sitting there, because it's an opposing thing. So the EMF is sometimes even called the back EMF, like backward. Now, how can Lenz's law be understood better? All right.
May you define the word induced again?
Induced, what about?
Yeah, like was induced.
Induced means like created in.
Just like made.
Made, yes.
Okay.
Yeah. But that the current, of course, is not. That's why Lenz's law. I'm talking about Lenz's law now.
Okay.
That is not generated out of nowhere.
Okay.
That's what Lenz's law actually came to understand.
Okay.
So what Lenz was trying was this. At least mentally he was trying this. Now this is a coil.
Looks like a solenoid to me.
Yeah. That's a coil. And that's a galvanometer. Now pay attention. Tell me right now, this is a magnet, right?
Yeah.
If I have to move this magnet from here to here, do I have to do work?
No.
No. Why?
So it's on the same.
Perpendicular. So the force that I'm applying right now is to just carry it, right? Which is mg. And which way am I displacing? Sideways. So force and displacement are perpendicular. So did I do work when I did like this?
No.
No. So if I'm moving this magnet from here to here, am I doing work? No. Correct? I did no work, but electricity is generated. That's against law of conservation of energy. How can you create electrical energy by not doing work? You understand? So what Lenz was thinking was like, that's not possible. In terms of physics, yeah, I'm not doing work, but electric energy is generated without doing work. That's impossible. So he just tried to do it a little more carefully. And what he noticed was this, that when he was pushing it inward, that thing was pushing the magnet outward. So he had to do work. You understand? Mm-hmm. So when he was pushing it here, he was feeling a force of repulsion. And when he was pulling it out, he was feeling a force of attraction. Oppose the cause. So when he was coming to the right, that was pushing him to the left, so he had to do work. When he tried to withdraw and go to the left, that was pulling him to the... So what lenses finally found out is, okay, now I understand why the electricity is generated, because I'm doing work. And so my work is transferred into electrical energy. Did you get it?
Yeah.
So even when I push this magnet in, when I get closer, I feel an opposition, a gentle opposition when I get here. And when I pull it out, I feel an attraction. I can feel it. So that little work that I do is the cause of the electrical energy. Make sense? Now let's investigate this a little further. If this is a north pole that is coming in, see the magnetic field of the north pole is here. How can you oppose a north pole? Which way should the current flow here? Now, this north pole is coming closer. So this must act as a north pole, right?
Yeah.
Use your right hand grip rule.
Stop it.
This is the magnetic field that you want. So which way should the current flow? Like upward?
Yeah.
That means here. So the pointer will deflect to the right. But if I keep the magnet fixed in one place, am I doing work?
No.
So the pointer will come back. So the pointer will come back again. Now let's say I'm pulling this magnet away. If I'm pulling the magnet away, this is a north. So if I'm pulling the magnet away and you need opposition, this side must be what? A south. So if I have to produce the south over there, the north must be on this side. So the current must be flowing down, which means the current must be flowing this way. So the pointer will deflect to the left side. Make sense? So that explains why the pointer was going opposite directions.
Sure, my dog.